Great. Hi, everyone. I'm Stacey Naeemullah. This summer, I worked with Dr. Yang Song, Dr. David Wright, and Dr. Ayumi Fujisaki-Manome on a project looking at developing machine learning surrogate models to improve rapid prediction of oil-affected water areas. A bit about myself first. I'm originally from New Orleans, Louisiana, and I recently completed my master's in physical oceanography at the University of Hawaii at Manoa, where I studied air-sea interaction in the eastern equatorial Pacific. For this study, however, we are looking at the Straits of Mackinac, which connect Lakes Michigan and Huron at the northern ends of both lakes. Combined, these lakes are a very large body of water. The Straits of Mackinac themselves are about 6 kilometers wide and 30 to 80 meters deep. Hydrologically, they're very interesting. They have reasonably swift currents and a peak volumetric flow rate of 80,000 meters cubed per second, which is on par with major rivers. That's a peak, not an average, but it gives you an idea that this is a dynamic system. Additionally, it has an oscillating flow. So the current changes every few days from east to west, west to east, and seasonally it's stratified, so it's going both directions at once. As a physical oceanographer, I'm very fond of this feature. It's very interesting to me. In addition to the dynamics of the hydrology there's also a fair amount of human interaction at the Straits of Mackinac. There's a bridge that is crossed by 3 million vehicles a year. More than 2,000 commercial vessels transit the Straits every year. And that's in addition to all of the personal and recreational vessels that are utilizing that waterway. Also, there's a large oil pipeline. Well, it's two pipelines with 20-inch diameter that carry up to 23 million gallons of crude daily between Superior, Wisconsin, and Sarnia, Ontario. And they cross the Great Lakes at the Straits of Mackinac. They run along the floor of the Straits. They were originally constructed in the 1950s with a 50-year lifespan, which we've exceeded by a few decades at this point. So Enbridge is talking about replacing the dual pipelines with a single larger pipeline that's housed in a concrete tunnel. But until then, there is the aging pipeline in place that has never had an actual oil spill, but it's been struck by anchors from commercial vessels. There's been subsidence underneath it. Oh goodness, sorry everyone, my camera fell. Apologies. So there is concerns about oil spills in that area. If there were an oil spill, they're affected by multiple simultaneous processes with different timescales. So the first concern is the chemistry. Is it light crude, which floats, which is what it is in this case. Heavy crude has resins and sinks. Additionally, there's the meteorology, so the air temperature, the wind speed, the sun, the hydrology, currents, water temperature, geography, so the materials and the roughness of the coastlines and the bottom. And there's also microorganisms. So all of these things affect the transport and fate of the oil particles. Currently, NOAA has a high-fidelity numerical simulation model called NOAA, which can model oil spills. It is a Lagrangian model, so it follows the trajectory of the particles and models the transport of the pollutants based on input features of the forcings. So I think they're called movers and weatherers in the model. There's a web suite and there's also a Python package. I've got just some images that I took directly from the NOAA website, from the web suite, where we've got a chart that shows how the model is predicting the fate of particles at certain time steps. And then on the right, we've got what a particle spread looks like coming out of the model. That's not the Straits of Mackinac, that's Mobile Bay in Alabama. For our purposes, we use the GLOS output, which has a 3-day runtime for Lakes Michigan and Huron. So here's some images of a hypothetical oil spill in the Straits of Mackinac at 24 hours after the oil spill. The particle locations are pictured in red. And the shaded areas are sea ice, or lake ice. And what we can see is in the first column, those are the winter months where there is ice on the water. The particles aren't really translating anywhere. Whereas the rest of the year, we do see the particles moving and spreading. So ice does impact how oil spreads in the environment. On the top left chart there, we have the hours elapsed and the oil spread. So each of those lines, we go 6, 12, 18, 24 hours, and we can see how the oil particles spread in the NOAA simulation. And that's the average per month. And what you can see in the winter months, January through March, is there's significantly less spread than there is the rest of the year. And there's a peak in April that we think has to do with ice melting and all of the interesting circulations that go along with that. In the bottom chart, we're looking over time between January 2023 and April 2025. And the gray boxes on that plot are showing the average of the 24-hour oil spill area during the winter months. And January through March 2024 was a unique winter because there was very little ice. And so we see that the particle spread is significantly higher in that period than it is in the 2023 and 2025 winters when there was substantial amount of ice. So we know that the ice is affecting where the oil particles are going, not other winter processes. And the fate of oil particles when there's ice on the water is generally believed that, the ice either physically blocks the oil from spreading, the oil can get trapped underneath the ice, or can be encapsulated inside of the ice. When we look at other initial conditions, wind speed, currents, flow velocity, and ice, we can see that the relationship between the forcings and the output is complex. So what we're looking at in these charts is the oil-affected water area after 12 hours compared to the values of each of the initial forcing conditions. In the top row there, we have the current in meters per second, and then the wind speed in meters per second, followed by ice, which we've just discussed. The concentrations, you can see there's a lot of data where there's no ice. That's the rest of the year. And then the far right column, we've got the meridional and zonal wind speeds. Zonal is on the bottom. And then in the bottom row on the left, we have the eastward flow velocity followed by the westward flow velocity, and then the north-south flow velocity. And while we do see some coherence in the relationships, they are very blobby. And so we know that there's a complexity to this relationship and a fair amount of nonlinearity. And the question is whether we can use machine learning models, which are process agnostic, to train ensemble machine learning or simple machine learning models and provide similar results with reasonable accuracy. One reason to do this is it's a lot faster. It is also just a thought case. If for runtime, if we look at the GNOME's model, it runs in about 8 seconds, which is fast, right? The machine learning models run in 2,000ths of a second, so it's an order of 10 to the 3 difference. So if you imagine it on a larger scale, or just for rapid response, the pre-processing of the machine learning data is also significantly simpler than the pre-processing of the GNOME's data. Machine learning can provide us with the scale and the classification of the event, but again, we don't know much about the actual physics. We looked at 4 different machine learning models, 2 simple models, 2 ensemble models. The first, what is machine learning? In this case, regression machine learning is we're just looking for the algorithm looks for a rule that connects inputs to target outputs. So you've got your vector X, you apply function F, and your output is vector Y. Ensemble machine learning models combine multiple machine learning models in order to reduce overfitting and underfitting and better improve accuracy. And the general rule of machine learning is that the outputs have to be predictable. So you can put in random data and machine learning will tell you a relationship. It will provide a rule, but that rule will be only applicable to that exact set of data. When we look at the first simple model, ordinary least squares regression, everybody's reasonably familiar with that. That just is assuming a strictly linear relationship between your input forcings and your output, and minimizing the mean square error. The second simple model is the k nearest neighbors, and that uses the proximity of the forcings. So each forcing, what are the k nearest neighbors based on Euclidean distance, and you normalize the data first so that you don't have weird weight issues. And then based on those k nearest neighbors, what are their target output data, and takes an average and produces a result. This is also not an ensemble model. Random forest is our first ensemble model, and that just makes a series of decision trees that are independent. So it takes a random sample of your test data, and it selects random forcings and determines areas of sparsity and density in the data to create nodes, which are basically thresholds, over, under, that's the splits in the decision tree. And it makes many of these trees, and then the prediction from each tree is averaged. And finally, we use extreme gradient boosting, where it makes many sequential decision trees. So it runs a bit slower than random forest. And each decision tree minimizes the gradient of a cost function in order to reduce the error compared to the prior tree. And then they are all aggregated together using what's called a learning rate, where the earlier trees have heavier weight in the final output than the later, more fitted trees. This reduces overfitting and produces a better result. In terms of prior research, when we're talking about oil spills in freshwater with ice and using machine learning models, that's a very broad, because you've got, oil spills, although most oil spill research is done in marine environments. You've got machine learning, which we have freshwater and marine environment data on. But there's no observational oil spill data or studies from the Great Lakes. So most of that is simulated with models like gnomes or with drifters. So our first surrogate model is we looked at whether machine learning could accurately predict just the scale of a contamination event. So looking at the area encompassed by the individual particles in the gnome output, can we predict a similar area using machine learning? So the forcings were the time average values of currents, wind, and ice concentration. And the target was the oil affected area in kilometers squared at 6-hour time steps. So with these plots, we've got the 4 machine learning models and their fidelity to the actual output. The horizontal axis is the affected area from gnomes, and then the vertical axis is the predicted affected area after 6 hours. And the first thing we see is that they all actually produced reasonably good results, even the ordinary least squares. The random forest and extreme gradient boosting ensemble models performed perhaps slightly better with lower mean average error, but the R-squared values for all of them were reasonably similar. At 12 hours, the models performed a little bit worse, in particular the ordinary least squares, but they're still reasonably good fits. We do see that at the larger spread simulations that we have a bit of overprediction in the machine learning models, and that's probably to do with the fact that they're outliers to begin with, and we're trying to predict outliers. But for the bulk of the data, we have a reasonably good fit. At 12 hours, the R-squared values degrade a little bit more, but less than they did in the prior time step. The ordinary least squares is falling off the most, and we have the best performance out of the ensemble models with mean average area right around 7.1 kilometers squared. And finally, at 24 hours, we're still seeing R-squared values at 0.65, which is reasonably good. A little bit of overestimation still, but promising results. Goodness, I'm sorry, everyone. My camera is not stable here. So what we found is that the data-driven models do show promise for improving the rapid response guidance for contamination events in the Straits of Mackinac. There's some benefits because the pre-processing is simpler, the runtime is faster, and especially when we're talking about early response, this provides a reasonably accurate estimate of the scale. So what supplies need to be mustered, what needs to be put in place to get ready to respond to this event in very short order. For future research, we'd like to look at the geographic extent. So where are the specific particles located at each of the time steps? And can we estimate the output of the Lagrangian model by particle? And we've got some initial results in the image there on the right. The blue dots are the model prediction, the red dots are the blue dots are the surrogate model prediction, the red dots are the no model predictions. And we can see reasonably good accuracy at this point, and with still that odd overestimation problem at the larger extent. We also would like to include diffusion processes in the study and start exploring the surrogate models, understanding of or interpretation of the physics using feature ranking analysis packages. So many thanks to my project mentors. This has been a very interesting project. I've enjoyed working on it very much. And altogether, the summer has been a very good experience for me. Many thanks to Margaret and Mary and everyone at CIGLR. And are there any questions?
All right, great job, Stacey. Thank you so much. And we've got time for a few questions before we take a break.
Hi, Stacey, great talk. You anticipated this question about diffusion processes. Am I right in thinking that NOAA probably doesn't represent diffusion because it's particle-based? I think, I've seen some particle trajectory simulations that sort of simulate diffusion with a little bit of random noise. So if that's the case, if NOAA doesn't have diffusion, how important do you think it is as a process, and how would you go about incorporating that? Happy to just hear your speculation.
Sure. So I believe, sorry, there's an echo. I don't know if we. So the NOAA model does take into account subgrid diffusive processes, I believe, but I think I'm not certain how it does that. Whether that's numerical or if it's just an addition of randomness. In terms of incorporating it into this model, there are a few papers that I have found in a literature search and a few that Dr. Song has shared with me. And I have not looked into them just yet, but that is something I'm going to work on this fall.
Okay, sorry about that, Stacey. I had a technical issue. Next question.
You have 4 methods there, and the last one looked like more dispersive. What is the mechanism there? Is it because of the methods or because of the forcing data or something? Forcing the same.
Do you mean the XGBoost model?
Mm-hmm.
Yeah, so that's the overestimation, and we actually saw it when we were just trying to look at the scale of the oil spill events as well. So we saw that it tended to overestimate the kind of the outliers at the higher end of the range of oil affected area. It's nothing I've looked into too very closely because this image, it is confusing to look at, but the density of the results is hidden by the red dots from the original simulation. And there's far more of the predictions that adhere closely to the original simulation than there are the outliers that are very visible in this plot.
Okay, and it's possible to do some of the sensitive study. For example, you remove the wind forcing or remove the ice cover or something. You have a 3 forcing, right? You can you can do the sensitive study by removing 1 forcing at a time.
I haven't done that, but that is something we can do. There's also like I said, the feature ranking analyses can give you an impression of how much each of the forcings affected the final output, like how much impact they had on the final output.
Okay, thank you.
Okay, thanks, Gia. Do we have any more questions for Stacey? Sounds like we have one online.
All right. So Ellen says, thanks for this great talk, Stacey. The model comparisons at 6H show a gap in data points at the lower end that isn't clear at other time points. Why is that?
That's a good question, and it is something that we've looked at and discussed, and it is completely escaping me. So I don't know, Margaret, if you could share Alan's contact information with me, I will look back at my notes and get back to him.